Hello, my name is Kareem Khalifa, and today's lesson is methods of proof. Here's the plan of attack. First, I'll explain why this matters. Then we'll talk about the basics of proofs, basically that they involve a series of valid inference steps. Then we'll look at a few special methods of proof by cases and proof by contradiction. And finally, we'll look at what happens when you have an argument with inconsistent premises. Let's begin by discussing why this matters. We've now encountered two different ways of achieving the main goal of this course, that is, ascertaining the validity or invalidity of a given argument. First, we've looked at truth tables. The virtue of a truth table is that it's a mechanical procedure for ascertaining validity. If you follow the instructions properly, you will always know whether a given argument is valid or invalid using the truth table method. However, truth tables have two major drawbacks. The first is that as soon as you start to have arguments with lots of atomic sentences, they get really unwieldy, right? So 4 atomic sentences is already 16 rows on your truth table. Obviously, it just goes up by powers of 2 from there, so 32, 64, etc., as you get more and more. But often we reason with several claims at once, several atomic sentences at once, so that's a real limitation. The second limitation of truth tables is that they actually aren't very effective for communicating why an argument's valid or invalid. People need to be well versed in what a truth table is and understand validity and so on and so forth. This is actually not how we typically reason when we're communicating with one another. Our second method for ascertaining the validity of an argument was using proofs, and we've just scratched the surface of this. Now what you're going to see is basically this has actually none of the drawbacks of the truth table method. You can use as many atomic sentences as you want, and you aren't really constrained in quite the same way as you are with the truth table, and it's a little bit closer to how we actually reason when we're communicating with other people. Today we'll dig just a little bit deeper into proofs, but it's really going to be an ongoing process throughout the semester. The guiding idea behind a proof is that every step from the premises to the conclusion is a valid inference. Recall the earlier analogy between proofs and games. Just as you have an initial field position and you move down the field towards the goal in accordance with the rules of play in something like football, you start with premises and move towards your conclusion using basic rules of inference. So to tie this analogy to the current point, each step down the field, as it were, is a valid inference step. These valid inference steps are governed by the basic rules of inference. Thus far, we've only learned about 2 basic rules of inference: identity elimination and identity introduction. We're going to learn about a few more today. For today, I just want you to get a feel for these rules. Hopefully they just feel like valid inference rules. You can even test them very simply using your truth tables. Going forward, we'll regiment them a little bit more and show how they play out in actual proofs. And this is where we'll use Fitch to really sort of regiment our thinking in a tight way. Our first new rule is called conjunction elimination. This says, from P and Q, infer P. Here's just an everyday example. Take our friend Megan Rapinoe in this picture over here. She both plays soccer and is from California. Therefore, we can infer that she plays soccer. Our next rule is conjunction introduction. This is basically the mirror image of conjunction elimination. In conjunction elimination, you had a conjunction from which you inferred one of the conjuncts. And in conjunction introduction, you have both of the conjuncts from which you can infer the conjunction. All right, so suppose we're given 2 independent facts. Megan Rapinoe plays soccer, and furthermore, Megan Rapinoe is from California. From that, we can infer that Megan Rapinoe plays soccer and is from California. So you see, we're introducing and in line 3, hence the name of the rule. Our third rule is disjunction introduction. This says from a single disjunct, say P, you can infer the whole disjunction, P or Q. For example, from the fact that Megan Rapinoe plays soccer, we can infer that Megan Rapinoe plays soccer or plays tennis. Now you might look at this example and say, hey, where did we get this play tennis bit from? Or more generally, when we look at the rule, given that we have P, where did Q come from? And this really speaks to an important point that we should hammer home now. The reason that this is odd is because we very rarely would want to assert P or Q if we already knew that P was the case. It's sort of like being cagey. For instance, if I know full well that Megan Rapinoe plays soccer, but I only assert that she plays either soccer or tennis, it looks like I'm being uncooperative as a communicator. However, the crucial bit is that this is a valid inference step, and that's really what we're trying to hammer home. Remember, this is an artificial language, so it's not going to do everything that we want a natural language to do. So in English, we wouldn't typically use disjunction introduction, but if the purpose of the language is actually to highlight the validity of certain forms of reasoning, then it makes perfect sense that this would be the kind of rule that allows us to move down the field, if I can go back to that analogy from before. Next rule is a little bit fancier. It's what's called or elimination, and it's nicely captured by that saying that all roads lead to Rome. And that's the core idea behind disjunction elimination or proof by cases. Okay, so here's the rule stated abstractly. Suppose you have a disjunction which can be arbitrarily long, so either P1 is the case, or P2 is the case, or P3 is the case, etc., all the way to Pn. And suppose furthermore that you can infer S from P1, and you can also infer S from P2, and so on and so forth, all the way through Pn. Right? Well, then clearly, all roads lead to S, so you can infer S. Let's illustrate this with the simple case in which there's just two disjuncts, right? So there's either P1 or P2. We can represent that as there's two possibilities with this branching structure that you see here. Next, note that it says S can be proven each from P1 and from P2. Therefore, all roads lead to S. Proof by cases is implicit in another famous saying, you're damned if you do and you're damned if you don't. Basically, those are the only two options. Either you do something or you don't, and in both cases, you're damned, so you know that you have to be damned. Uplifting, I know. Our final new method of proof, or rule of inference, is proof by contradiction, what's sometimes called negation introduction, and also sometimes called indirect proof. Now, the general idea behind this is if you want to prove not S using this method, you assume S, that is the exact opposite of what you're trying to prove, and show that there's a contradiction. We represent contradictions with that upside down T that you see there. You may have encountered proof by contradiction in your math classes before. However, you can also do it with non-mathematical inferences so long as they're valid. A perfectly nice one comes from the Mueller report. You guys may remember this very famous line from the Mueller report in investigating President Trump. It said, if we had had confidence that the president clearly did not commit a crime, we would have said so. Clearly what this is saying is that the Mueller team did not have confidence that the president clearly did not commit a crime. So we can treat this as a proof by contradiction. Let's see how it goes. So first assumption, if we had confidence that the president did not commit a crime, we would have said so. That's going to be the starting point for the proof by contradiction. We're just going to treat that as a premise in our argument, as the Mueller team did. Next, take note of the strategy suggested by the rule for proof by contradiction, right? We have to assume the opposite of what we're trying to prove. So what we're trying to prove is that the Mueller team did not have confidence that the president did not commit a crime. And so we have to start off with the assumption that they did in fact have confidence that the president did not commit a crime. Next, notice what follows from those two claims, right? If we had confidence that the president did not commit a crime, we would have said so, but we're assuming that we did have confidence that the president did not commit a crime, so we would have said so, right? However, because they're using would, that is, they're using a subjunctive, we know that they did not say so, and in fact, if we looked at the report, we would see that they did not say that the president did not clearly commit a crime. So we have our contradiction. We're now in a position to draw the conclusion that the Mueller team did not have confidence that the president did not commit a crime using proof by contradiction. As you can see, we've assumed the opposite of what we're trying to prove. And using that supposition, or that assumption, we found a contradiction. So we get to infer our desired conclusion. And using that supposition, or that assumption, we found a contradiction. The last thing that we're going to look at today are arguments with inconsistent premises. Now these are really weird on some level, but here's the crucial thing to know. Any such argument is always valid. This means that anything follows from a contradiction, which is pretty strange when you think about it. First, let's just see how weird this thing is. This is going to be a valid argument according to the system that we're using. John stole the car, John did not steal the car, therefore unicorns exist, right? Super weird. So now let's explain why it's valid. As you may recall, an argument is valid if and only if there is no possible way for all of its premises to be true when its conclusion is false. As you may recall, this is very important. Next, observe that if an argument has inconsistent premises, like this one involving John, who may or may not be a thief, then there is no possible way for all of its premises to be true. Now note the overlap between these two statements. Obviously, if an argument has no possible way for all of its premises being true, then there's no possible way for all of its premises to be true when its conclusion is false. Right? So it follows from this that any argument with inconsistent premises is valid. So at this point, perhaps you're losing your faith in this logical system that we're learning. Why does it license such weird inferences? Why does it call these things valid? I'm going to give you two reasons to think that this is not such a weird consequence after all. First, although we're focusing on validity, what everyone really wants are sound arguments, and it's impossible for this argument to be sound. There's no way that all of its premises can be true, even though it is in fact valid. So there's a perfectly good diagnosis for why this is a bad argument. Second, the notion of validity might in fact be the correct verdict in this case. Here's a nice way to motivate that. Suppose that there's a witness in a court case and you're cross-examining them as a lawyer. Furthermore, suppose you get them to both say, John did steal the car and John did not steal the car. Right? That's a super unreliable witness. Anyone who would assert a contradiction would assert anything, including perhaps that unicorns exist. Right? So you basically get the right verdict from this as a result. Right? If anyone's willing to assert a contradiction, they're willing to assert anything. And that's exactly what this notion of from a contradiction, anything follows. In Latin, ex falso quod libet. That's exactly what that intuition is capturing. So, wrapping up here, there are three main take-home lessons. First, proofs are more manageable and more effectively communicate our reasoning than truth tables. Second, we've introduced ourselves to many rules of inference or methods of proof: conjunction introduction, conjunction elimination, disjunction introduction, proof by cases, and proof by contradiction. Third, we've seen that arguments with inconsistent premises are always valid, but perhaps this shouldn't bother us too much.
Thanks, and I'll see you at the next lesson.